Okay, hello everybody. My name is Luca Matteis, and the first thing I wanted to say is thank you for inviting me. Of course, as I feel very humbled to be talking after Michelle and before David, which are two people I really much admire in the community, and I'm a sort of a nobody against them. But anyway, also wanted to thank you for inviting me to Finland, which I really, it's my first time in Finland, but I really like it. And even yesterday we had a speaker's dinner, and I found it really interesting how the variety, coming from Italy, the variety of food that you have I was really surprised, especially since you had cheese before dessert. I don't know if that's common, but for me it was a very interesting taste difference. And so anyway, so I'm going to be talking. It's going to be a little bit technical, so I'm sorry I'm going to dive into the details. But the title of my talk is Append-Only Development with React. And the title is a little bit up for, it's sort of put out there as a challenge. But essentially it's going to be talking about this paradigm called behavioral programming. And okay, so one of the things that I'm going to talk about the problem a little bit. So one of the things I stumbled upon this Hacker News thread maybe a week ago. And the title of the thread is why isn't functional programming taking over, okay? And I actually really like this comment. I know it's a little bit, but essentially one of the comments, which was not upvoted, so it was kind of down in the thread, but as you can imagine from the response, they're saying it hasn't taken over because programming languages are practically irrelevant to making products. From a reliability standpoint, Windows has always been a nightmare. It is still one of the most successful products of all time. It could have been written in Urdu, and no one would care. So here I'm challenging you to think a little bit about what is code, or what is software, okay? And the challenge I want you to think about is that essentially, no matter the tools or abstraction we use, having to maintain a complex artifact we call code seems to be the root of the problem. And what do I mean by that? Essentially, if you look at your any system that is made out of software, it essentially looks something like this, right? It's an artifact we call code, written in whatever language, and whenever we want to make changes, whenever we want to update how this system works, we end up having to look into various parts of this artifact, right? So whether it's code or a diagram, it doesn't matter. But we sort of have to look into several sections and update those sections, right? And this, in my opinion, this seems to be the same, even though we abstracted out so many languages and frameworks and ideas, concurrent programming, functional programming. This is essentially how we've been doing it for ever, since programming has been invented. So behavioral programming challenges this. So the general intuition of this paradigm that I'm talking about is that what if we could make changes or understand how complex systems work without having to read, maintain an artifact, or maintain an artifact? So I know it's very abstract, so I'm going to jump into so this is the intuition. Instead of this is why my talk is called append-only, because the intuition here is that we can feed a complex system these so-called scenarios or things that we want to see happen in the system, and then the system just makes them work, okay? And this is the paper that I sort of got inspired from, and I'm trying to bring it to the React world, I guess. And it's written by these very famous academics. David Harrell is the creators of state charts. Anyway. So I'm going to try and explain to you the thing that sort of blew me away when I first learned about this paradigm. I don't know if I can stop here. And essentially the way that it works is that we are going to program using these things called B threads, okay? And these are these yellow boxes on the top left. And essentially they're called B threads or behavioral threads because they run in parallel. And from a JavaScript point of view, these are essentially function generators, okay? Even though this is an implementation detail, I want you to think of them as function generators, okay? And essentially, they can do three things. and these are the colored things I want you to also remember the color. So they can request for an event, so they can sort of yield the fact that they're requesting for an event. They can wait for an event in green, and they can, more uniquely to behavioral programming, is they can block events, okay? So again, try to remember these three things. And also remember that events in this paradigm play a crucial role, okay? So it's all about coordinating events. And I'm going to show you an example. Now here we have, imagine this is the body of a function generator, okay? So how many of you know what function generators are and what about the yield? Lift the hands. Okay, so essentially you know that a function generator can yield specific things. In this case, we're yielding objects, okay? But they can yield whatever. And essentially the difference from a normal function is that the execution is controlled from the caller, from the outside of the function. So we can control when to execute and how. Sorry, just when. So here we have, I want you to pay attention to what this function means to you. So when you read this function, it's essentially an infinite loop, okay? And what it's doing is I want you to pay attention again to the keys of these objects. So it's waiting for an event. So the string are events in this case. So it's waiting for the event water level low, and then it's requesting 3 times the add hot events. So if you look at the event trace on the right, essentially here, when we execute this generator using this behavioral programming system, essentially the execution stops at the step, right? Because the semantics are saying that it wants to wait for this event. So we have this yellow line, and also this yellow line is very important. I want you to pay attention to it because it describes where the execution is in these functions. And essentially, whenever the water level low happens in the outside world, so maybe it's triggered by something else, by some other system, we have simply the generator or the function continues its execution, right? And the add hot is requested 3 times. This is nothing surprising, And I can continue. Here I'm adding another thread to the right. So the one on the left is the same as before. The one on the right is a new one. And again, here it's nothing surprising. If I continue the execution as before, water level low is executed. Happens from the outside world. They both continue. So now I want you to pay attention to this line, and this line is connected, and that's important. I'll show you why in a second. And nothing surprising, the left one starts executing first because it appears first, so it requests add hot 3 times, and then add cold is requested 3 times. So the behavior of this program is essentially that whenever water level low happens, we request hot 3 times, and then after that we request cold 3 times. Nothing surprising. It's pretty. Now here's the thing that I hope it's going to blow you away in a way, maybe not. We're going to add another thread, okay? Another B thread. Again, I told you these things are called B threads. Now this new one is as before. It's still a generator, so we're going to see its execution stop at the first yield statement. However, this time we are introducing this new red thing. It's called the block. And essentially what's going to happen is that whenever water level low happens, the one on the left continue their execution. However, this is why the yellow line is connected, because now what's going to happen is that every time this line moves across all the B threads, we're going to check and we're going to interrogate all of the B threads to ask which event should be triggered. Okay, this is the general algorithm behind the system. I hope it's clear. I don't know, maybe I'm losing some of you, but anyway. So if I execute these B threads as before, there's an interesting outcome, and I want you to pay attention to the event trace. Now, the event trace of the program is essentially interleaving the 2 events. So it's changing. It's effectively the main difference here is that by simply adding a new B thread, so by appending or adding a new code, we change its behavior, okay? So imagine implementing something like this or changing the behavior of a system by only adding new code, without having to go back and change old code. So this is the main insight that I want you to think about. So I'll continue. This is just a diagram of how it works. We can actually give names to these B threads. So there's, when low add hot, when low add cold, and the last one is stability. And we can remove each one, and they work independently. Now, I want you also to, sorry, I'm saying a lot of times I want you. I don't want you to do anything, but if you can think of what is the event trace, okay? So an event trace, in a way, describes the behavior of a system. So if you're familiar with something like Redux, I think Redux actually is quite important because it allowed us to think of changes in the behavior through these serialized objects that we can read. And I think that's extremely sort of breadcrumbs of things that happened. But anyway, so event trace, essentially here I have an ATM system, okay? And you can imagine as things happen, as users, like imagine we have no access to the source code of the system, okay? So whenever things happen, we still get we're able to see what's happening the only way we are able to understand what's happening within the system is through this trace, which is telling us what happened. We inserted the card, the system then validated the card, it loads the account, and the account loaded, et cetera, et cetera. Now, imagine we want to change, again, same thing. Imagine we want to change the system. Imagine a new requirement comes in. And this requirement, as you see at the top, we want to show the advertisement before the account is loaded, okay? So think about how we would implement this requirement using a normal paradigm. We would essentially have to go and dig into code and understand, okay, where is the part of our code where we're loading the counts? We would have to go there, change that in lines of code, and add this functionality. Here, instead of looking at the code, again, forget about the code, forget about the artifacts, let's look at the event trace. So how can we implement this requirement with the event trace? Essentially, the goal of this requirement is that we want the event trace to become something like this. So we want to add these two events because we want to show advertisement before loading the accounts. So they have to happen at this section of the event trace. Now, if you think about this, we can do this using the system that I just described. And by using these two B threads, as I showed you before, again, without even knowing or caring about how the system is doing its things, by simply adding these two B threads, as before, as I showed you with the example, we get this, the trace of events that happen. And whenever there's an event that the threads can react to, they will react, it's shown here. They will continue its execution as before. And as before, this imaginary yellow line is going to dictate what is the event that needs to be triggered. And because the new code that we added is saying that it needs to block loading account until the add is shown, because that's the requirement, that's exactly what's going to happen. And we will see the event trace become what we intended, okay? So it's entirely a game. Programming this way, it's a game of figuring out what needs to go in the event trace, what shouldn't go into the event trace, what should not happen. So kind of different way of thinking. And again, here I have another example with another requirements where we don't want to show the advertisement if it's an enterprise user. So when it's an enterprise user, we have this new event called isEnterprise appear in the event trace. And essentially, this is what we don't want those two events that we just added. We don't want them to happen when the enterprise event is triggered. And again, this becomes a game. I'm not going to go into detail, but it becomes a game of blocking and waiting for other things to happen using these B threads and having this imaginary line. Okay. So the main insight is that newly added code can change how old code is executed. Okay. Okay, so let's play Tic-Tac-Toe. I have another example. And actually, this one is built in React, so I'll get closer to React in a second. But essentially, if I start playing, this is a simple React board where you can draw X's and O's, and as events are triggered, things are drawn on the board. Sorry, if I can open this water. Now, the game works, and it's fine. I mean, but if you look at the outcome of the thing that we just clicked on, certain things shouldn't happen by the rules of the game. For instance, as you can see, there's a trace where, for instance, two X's are allowed one after the other. But that's not really how the game is supposed to work, right? The game of tic-tac-toe works that there's one X and one O, okay? So essentially, the change that we want to have in the system, that we want to make happen in the system, is that we want to force that event trace, not the one on the left, okay? And by doing that, we can do this with this sort of append-only way, by adding this B thread that waits, and if you can read this B thread at the bottom, it's called enforce player turns, and it does exactly what I just explained. You know, there's again this imaginary line of execution that appears, and whenever we draw an X, it moves to the next statement because that's what it says. But now it's blocking an X. So in fact, if we try drawing an X again after an X, it's not going to work. It's going to only work with those. So I hope you understand the mechanics of this, okay? And this is just sort of the outcome of how this works right now. So here it's trying to draw O, and it's not working because, sorry, it's trying to draw an X, excuse me. It wasn't working because we just draw, so there was the B thread that was blocking that statement. So this is an interesting way of programming, I think, and it really, in my opinion, it really changes the games on the table. Like, for me, I know it's hard to grasp, but I've been studying it for maybe the past 6 months, and it really changes how we think of software in a way. Like, again, having not to think about the artifact, only having to think about the behavior. It's really interesting. But how do we use it with React? It turns out, actually, that in a way, I don't know if you can read this, but in a way, the React components can be thought of as a B thread. So one of these things these function generators. And now I introduced some syntax here, like this update view, but essentially, this on the bottom here, we're using connect, which is part of a library that I will tell you about. But essentially, it's describing the state changes for this component using the same yellow line execution steps. So whenever an event happens, the line changes its position, and certain things happen. For this case, what happens is this update view function is called, which makes the component change. So we're changing it from a button that has on-click handlers to just a button with the X or O on top of it. And this is how you render them. You render them with this, there's of course a provider. So essentially in this system, all the events, like I told you before, become first-class citizens. So they're global throughout all the B threads. And it's important that they're global because they need to know if there's a B thread that is blocking an event, using, again, this imaginary line that we ask all the B threads for what's being blocked. Okay? And again, so we can think of it, these components, these are 9 React cell components. If we can put them like in our minds next to each other, as we did with the B threads, we can draw this imaginary line, and whenever this line changes, the state of the components also change in a way. So this is sort of the abstract idea. And here, just as an example, I want to show you that you can actually build pretty complicated React applications using this system. I have this very simple, movies app where it shows you the current movies, and you can click on things, and on the right, there's the event trace, as I showed you before. At any point in time, we can look at this event trace and sort of ask ourselves, okay, is this something we want to see in the system? Do we want to change how this event happens or when it happens? And we can do this playing this little game of adding B threads and having this imaginary line, yellow line, change the order of things in an incremental fashion without having to even... So here I can, for instance, look at the bottom 3 events and ask, okay, maybe from a business point of view, these are not supposed to happen. Okay, instead of having to dig through code, I can just add this B thread. Okay, so again, the event trace is actually the behavior of our system. and making changes to these projects that didn't require us to understand how they were implemented. We simply fed the system with new scenarios and the event traces we wanted to see happen. Oh, sorry, on the event traces we wanted to see happen. And from an abstract point of view, this is very much in line with how humans think, I think. So you can imagine these two things, okay? So imagine we want to have a 6-day trip from New York to Los Angeles. On the left, we have sort of the driving directions, right? I want to start driving, I want to merge. These are only things that are related to the directions. And this can be sort of developed by a team on its own, right? And on the right, we have the daily schedule. And these are things that are only concerned about the daily things, what to do, like stop the car, look for a restaurant, things like that. With this behavioral programming, essentially, what it's saying is that it can take these two scenarios, so these two B threads, and through this interleaving that happens at runtime, using this yellow line that I showed you, we can actually get the behavioral outcome, which is, again, a 6-day trip from New York to LA. And finally, now that I've sort of explained this, how it works a little bit, if we go back to how we program, okay, how we currently program systems, no matter the abstractions that we use, no matter the frameworks that we use, no matter the high-level languages, low-level languages, it doesn't matter. Like conceptually, this is what we do. We have an idea of how the system needs to change. Every time we want to see these changes, we have to change the code, and we have to look into these pieces. And for me, this is not really natural at all. And we've been doing this forever. And instead, what if we could do it somehow or somewhat more similarly to how humans think? What I mean by that is, again, let's imagine we have a system that is composed of several of these B threads, as I showed you. And let's imagine that we want to see something happen in the system. Now we can add, so append-only. And this new B thread can change the order of the old ones. And in fact, so we can continue this sort of pile atop kind of thing. And in fact, it arrives to the point where we don't even care about the old B threads anymore. Like, they can be a closed legacy system, and all we do with these new added B threads is simply change the order of the events or stop certain events from happening and changing the behavior of the system. So from a high level, again, from a high level point of view, I don't want you to read all this, but essentially, this is from a really great paper that I suggest you to read if you're interested in the subject. It's called The Quest for Runware. And essentially, what David Harel and Asaf Maran are saying is that in their vision, the units of specification and models are not assembled like resistors or chips, or perhaps like methods or fields in an object-oriented programming class. It's the interweaving of these behavioral models that will be facilitated by the reference of a common aspect of the system, like events, and not via mutual awareness and direct communication between components. Very abstract, I know, but again, it's essentially the idea where we can program using these scenarios that are then interwoven at runtime. So to finally conclude my talk, a few takeaways. Essentially, again, moving this imaginary line, which is actually called the synchronization points, but we can, by requesting, waiting, and blocking events, allows for this incremental type of development, where we can add things. And these B threads are aligned with the requirements and how humans think about behavior, in my opinion. And again, B threads are piled atop with no component-specific interface, connectivity, or ordering requirements. Okay. Now, of course, there's a few cons, such as this is sort of a very different way of thinking about programming. We have these events, we have to think about this line. However, I honestly think that more natural ways of programming, such as behavioral programming, are perceived as unnatural because of our past training. So I think actually because we're sort of stuck in this loop, maybe, where they teach us in school, or we're thought of just generally how to program in a specific way, that when it comes to learning something new that is maybe more akin or closer to how we think, it becomes unnatural. So does it scale with thousands or millions of concurrent B threads? Nobody knows. It's not very academic, but it's pretty academic. I haven't seen many open source projects. And again, there's not many people using it, and there's a lack of best practices, tools, and community, of course. So I probably would need some things from Michel, learn some of how he made MobX famous. And these are just some resources. So the first one is a link to the JavaScript library. Then there's a couple implementations specifically to React, which is what I showed you, and also Redux, which is a middleware. And I think the system actually works really well with something like Redux. And finally, the paper. So again, I think that's it. Thank you so much for the time. Thank you.